Hello everyone. I hope you guys had a good weekend, and today I will be talking about the model I have. I wanted to make this video today because tomorrow we're gonna have a meeting, so it seems good if I can show you these results I have since this weekend and we can talk about it. Excuse the time of the day. I was able to get it done and be able to prepare this video for you by this time, so I hope you get a chance to watch this video, and please let me know if you have any questions. The model I have is called the collision model. So the idea is actually very simple. We have two ships, and one is moving mm, vertically and one is moving horizontally, and you know, at this point, you could just say that if you can make the mathematical prediction, they're gonna collide. The idea I have here is very similar. I'm looking to see if we can predict cyberbullying based on what information we have from probability and statistics. This sounded a lot like a Poisson process, which we're gonna talk about a little bit in this video. Also, good to mention, this video is gonna be a little lengthy, so if you want to get your drink or whatever, feel free to do so. So in literature, the process is called survival analysis. So I learned that for biologists and engineers, there is a failure hazard function. So basically, it's something asking similar to what we have in the exponential distribution, where we say, given this time from, this future forecasting 10 days later, what is, how likely are we gonna have a failure? Now, in this case, a failure will be our object, the user, returning. So they're going to be posting something. So let me share my screen, and I want to show what I gathered and talk about this a little bit. So here I have the collision model, and I want to also talk about the outputs. So first of all, the outputs are going to be like this. Okay, we're going to get a posting rate, instantaneous posting rate for a user. Harm if a user posts. So this is actually a next step. We need to first say that given a user posts, so this is like a Bayes theorem, we need to know that a given property, given a user posts, how likely is it to be harmful? And then the next idea is, given a user posts and it is harmful, or you can just say harmful because we already assume it for the harmful case, how likely is this going to target the given user? In this case, the target will be we will be looking forward for a number of users for this case. There are a few issues with this part of the model. I'm still working on this, but I think the first two parts are promising enough for me to publish and share this with you, and I want to see what you guys think. Before we dive too deep into this, I want to talk about the survival function. So the survival function is a function that gives probability that a patient, device, or other object of interest will survive past a certain time. The survival function is also known as the survival function, whatever. It's it's I'm sorry, I don't think this was what I was looking for. Let me just pull that up real quick. I'm just gonna show you what I'm talking about. Weibull baseline. Okay, this is what I found. Weibull survival. Yeah, Weibull distribution. So this is basically a standard parameterization, a PDF of a function, and we're trying to see. Here's that formula. Yeah, the hazard function, so the failure rate. Oops, what happened? I got too excited. The failure rate of the function is given by this probability. So you can also look at this a little bit. I can send these links to you if you are interested, but basically saying that based on what information we have, if k is equal to 1, there is no effect on waiting for this event, so it doesn't change. And given that k is large enough, larger than 1, let's say k is 2, waiting increases the likelihood of the event happening, the failure happening. So in our case, I think k should be greater than 1, because the more we wait for a user to return, it is likely that they will return at a certain point. So if you wait, I don't know, 10 hours, and you say let's wait another hour, it's likely that it's increasing, like just like gambling. When you start gambling and you play, and then the next time you play and the third time you play, you have this idea in your head that, you know, the more I play, the more I try my shots, I'm getting closer to the failure rate, or the likelihood of me winning. So in this case, that's that. And these are other parameters. These are more hyperparameters in our case for lambda. We define a little different, but I'm gonna get to it. We define as theta and tau, and I'm gonna explain what those mean in a bit. So because I'm not necessarily done with this part, I'm just gonna briefly explain this. We're gonna talk about how I get the posting rate and harm if a post occurs. So let's read the abstract real quick. Online harm forecasting combines several different questions. Who is likely to participate? Whether a future message is likely to be harmful, and which users may be affected. These three properties. The collision model treats these as connected but separate prediction tasks. So these are separate tasks we are dealing with, but when we want to gather our outputs, we're gonna combine these ideas. So it is possible that we get lambda, or lambda and q correctly, let's say, or lambda itself gives a perfect result, but q doesn't. So naturally we're not going to get the best outputs, but the fact that we can get this correctly means we can fix these two and improve the model itself. It represents recent conversation history through exponentially decaying traces. The trace operator is something I mentioned that has a memory function. We're going to talk about that a little bit more in the future, so I'm just going to leave that. Models user participation with bound conditional intensities. Models message level harm with registered interaction between conversation, heat, and recent victimization. And models harm targets through a non-empty set target distribution. The design emphasizes chronological prediction, explicit censoring, calibrated probabilities, reproducible model selection in comparison with simpler baselines. The most important takeaway from this sentence is basically I'm saying, if I'm making a forecasting at time t, 10 o'clock in the morning, I need to know everything. I can only have information before 10 o'clock, naturally. I cannot just get information from the future. That would be incorrect and not a model. So the idea is I can have all the information from the limit approaching from the left to the time we're currently on. So if I'm at 10 o'clock, I can have information up to, say, 9:50, 9:59, okay, something like that. So it's only the information available to me at that point. So when we're testing with the data set, we have to do something about that. I know this question is going to come up, so let me just show this. I know what is the required data, what is the input. You can pause the video and check this. These are the inputs. I'm not exactly sure if a data set can potentially cover all of this. I think maybe one of them could, but if not, I'm suggesting maybe we should build a synthetic data set. But before, of course, we need to talk about this model. And I should have actually showed you this too. The paper explains stage 1 predictive model. So the stage 1 predictive model is basically predicting the basic properties like posting rate, post occurs, and others. And there are some other things might mention what stage 1 and stage 2 are different. in regards to the model estimates when a user posts and all of this stuff. So basically, before we jump onto the higher level predictions, such as open mode especially, we're gonna talk about closed and open conversation modes. These are gonna be our stage 1 outputs, and then if we can verify that stage 1 is working good enough, then we can move on to stage 2. So there are some steps we have for this. So let me just go back. These are the abstract, we just read that. Now let's talk about the scope, risk set, and events record. The model works within a conversation unit queue, such as a group channel or a persistent thread. This is to be interpreted as Discord. All right, Discord, WhatsApp, I don't know, even Reddit, but I'm not. As mentioned before, I'm not a really big fan of forums because I think the quickness of these threads make it harder to detect cyberbullying. So, especially as someone who also uses Reddit, I mean, I already had it open here. I use it all the time. I don't necessarily see online bullying almost anytime, and it's because usually these platforms are small enough that they can be easily monitored because every thread is not actually that big, and the timeline between messages are really large enough that even if someone sends a harmful message, they're not gonna the receiver, the supposed receiver, is not gonna see that message until maybe hours later. So by that time, a moderator can easily step in. But for a platform like Discord, I've witnessed a lot of different things happening, and people can do incredible harmful activities there. I've encountered a lot of instances, and those instances are where it's really hard to catch a lot of these things. For example, sometimes users would just create shortcuts for really terrible messed up words, and nobody would catch that really easily. I'm not saying we will, but what I'm trying to say is the fact that those platforms are quick enough that it's likely that a person is gonna miss it. So model actually is very useful for those platforms. Anyhow, a member U is considered at risk only during an observed membership interval. So a user must join the platform and leave the platform, where JU is the join and LU is the unit closure or administration. So LU, the leave time, is most likely going to be the leave time in our case. But if you want to think about cases where they close a unit, or the administration and the observation, those are also qualified to be leaving. And the risk set immediately before T is the user queue, the risk set. Users who have joined between these time intervals and they still haven't left. So the current time is less than the time they will be leaving the unit. All timestamps are stored in UTC. I will come to that point in a little bit, but the idea is this: at 4 a.m. for you, how likely are you gonna be to text in a Discord thread? I mean, there will be, of course, people. I mean, I'm not to say that that's a big hypothesis, but what I'm trying to say, it will have an impact for a lot of people. So if you're trying to model something like this, and we say that at 5 a.m. in the morning, we can give a likelihood of someone posting, like give a weight, basically, based on the time zone, and at 1 p.m., 2 p.m., or whatever, give a higher weight. So we're going to explain how we get those two, but the UTC is basically what we suggest because of the time zone, but I am aware that people from international zones could be in the thread. In that case, that's now not necessarily something the model addresses at this point, and it gets a little confusing when we deal with local time zones and multiple time zones. So since this is a comprehensive model, I don't think we need to deal with international zones right now. If this model works enough, anyone can just adjust it so that it will work for other time zones. Anyway, the message events is recorded like this. These are just some information. I'm gonna mention these as we see these things. This is important to know, that a harmless message has an empty set of TK. What is TK? Target set. Okay, the set of harm targets. So a harmless message will not have this, but by assumption, And this is what the assumption I initially had seems to be wrong, and I'm therefore working on it, is for this target probability of given harm, is the idea that if there is harm in a message, then there will be a target. So the empty set will not be existing. The target set will be a full set, and we are trying to find the targets based on semantic information we are given. I think that assumption is not true, so I don't want to start with that part immediately, but we're gonna look at that soon. So these are not necessarily what we talked about, so this is just having information we had before that time we are forecasting. Now these are the stage 1 and stage 2 properties. Closed mode is a condition on the currently observed risk set. So the risk set we're talking about is UQ, where people have joined and still haven't left. So we are talking about the users in this thread. The risk set and contains no membership changes during forecast interval. So they still haven't left in this forecast interval. A scheduled closure or departure known as a forecast origin is a deterministic boundary. An announced future departure is not used retrospectively. Closed mode is primarily a stage 1 setting. So we're assuming that we have a finite amount of people, and right now we're not gonna assume that people are coming in. Okay, and open mode is where we have a newcomer intensity, and we're going to talk about these in a little bit, but since I just want to emphasize a closed mode property first before even talking about open mode. So let's just go down. And deterministic updates. These are not inputs we are given, we're just creating these inputs. These are computed. How are these computed? Hold on. Okay, I'm recording. I just want to make sure. So these are trace functions. As you can recall, a trace function in discrete or integrate continuous, and we're going to talk about a continuous domain because we already introduced time variance, is basically the weight multiplied by e to the some function, some decay rate times a time difference. Okay, so these are traces. Take any trace you want, take e. Okay, so the trace is defined as a lazy update e of t plus delta equals to e t. So the function is just like a differential equation. We have e times the decay rate with a time interval. Okay, and these traces are also as you can see, a differential equation, so we can define these dotted variables. Okay, and what are these traces? The traces are AU, recent posting activity of user U. Okay, so a message, they send a message, we give a 1, add a 1 to their posting rate. Say Alice just posted, her rating was 5, became a 6. 5 minutes later, she still hasn't posted. For example, we have a half life, some kind of decay rate. It gets forgotten. Now it's at 4, at 3, at 2, and so on and so forth until it vanishes. So we have this kind of decay function for recent posting activity, JFV, JFU, JFV, U or V, these are just usernames from the given risk set. Recent direct attention received by user U through replies or mentions. Why am I adding a 1 here? It's because we're trying to define activity, right? Activity can be done by 2 ways. Either a user posts or someone posts to them, someone replies to their messages. So that also increases, that's also treated the same way as a, for each distinct reply to a mentioned user. If there is no harm, so basically the harm target set is empty, the harm related updates are given like this. The Z of KV and Z of KV message are basically just saying that these are the harm of the message they have. Okay, so E is the recent harmful activity in the conversation as a whole, so the message contributes to the harmful activity, recent harmful activity in the trace E. The message harmfulness contributes to the author's harmful messages score. VU is for victimization. We have a slow victimization history, and for DU we have a directed harm history. And RV, that's supposed to be just an empty space. Forgive this mistake. ZKV will be the harm. So fast recent victimization. So let me talk about these traces before we jump on too far. What is slow and fast victimizations? So I like to think of V of U, call this U or V, doesn't really matter, and R of U, like cousins or brothers or sisters or whatever you kind of call, because they're actually talking about the same thing. You have a slow victimization history of user U and fast victimization history of user U. So in one case, you're going to take a look at recent activity. User A has been targeted once in a thread. The fast victimization will be a quick decay function. At 10 minutes or 15 minutes, it's not going to record it anymore. It's going to be gone. But slow victimization history is where we will be saving this record, and we will know that this person has been targeted. Say maybe it will be a month, for example. So it has to be a month before we can erase that. So that's how it's updated. The slow directed harm is also another important property we have. We are given that a user, we know that a message targets someone. I was speaking with Dr. Artan the other day, and he suggested we use this as an input. So if I know that a message targets, say Bob targets Alice, that goes into the slow directed harm history for D if Bob directs Alice. Okay, and we're gonna have that history too. Why is this important? Well, if we know the history, it'll be easier when a Bob posts a harmful message. We're gonna now look at the candidates as who are gonna be targeted after Bob posts a harmful message. So remember how we go up. We talked about what? We talked about if a harmful post occurs based on the posting rate. So given someone posts, given Bob posts, and given that the post is harmful, what is a target probability of a given harm? So for a user, how do we know who's a target for this message without even knowing this message? Well, in that case, Alice will be a candidate because Alice has a history with Bob of being targeted, especially if Alice is active during that time. So we're going to talk about that a little bit more in this flawed part of the model. But yeah, one thing I should mention though before going too quickly is why are these three the most important factors of toxicity? Why did I pick these factors? Why not something else? Why not X or Y? The reason is because this. How does online bullying happen? What are the ingredients of online bullying? Well, number one, you have to have a person, because without a person you cannot produce harm. A person is who produces the harm. Thus we need to have the posting rate and harm of a post. And another thing is escalation and thread dynamics. So that also contributes. That's what I talked about, the two-ship metaphor. One is someone who is very easily provoked, and one ship is the thread is escalating. So these are the collision hypotheses, and I define a collision hypotheses mathematically. I wanna talk about a lot of things really quickly, but unfortunately these things take a little bit while for me to give the background. So these are just half-lives of suggestions of how we can decay these functions, decay the traces. These should be learned by machine learning hyperparameters, so I'm not an expert of these. I'm pretty sure there are people in this RU who knows all of this stuff really good, so I was hoping you guys could help me with the hyperparameters if you move forward with the model. Anyhow, participation through bounded conditional intensities. So let's choose a session cutoff. Okay, let's talk about a window. We want to say participation is separated into two situations: a user who posted recently and may continue an active session, or a user who has been silent for longer may return after inactivity. So two cases. Awesome post right now. In 10 minutes, how likely am I going to post? Well, it's been only 10 minutes since I posted, so I will give a probably higher rating than Awesome being gone for 5 hours and he hasn't posted since. So those are going to be something we're going to be considering. There are two types of defined participations here. either someone is active or not currently active. And tau be the user since you last posted. So if I posted 5 minutes ago, my tau u value, tau awesome, is going to be 5 minutes. If I posted 5 hours ago, likewise, tau awesome is going to be 5 minutes. So choose a session cutoff. Okay, 30 minutes, 1, 2, 4, 8. This means, how do I define activity? If a user posts right now, how long should they not be posting until I can consider them as inactive users? If these are also a parameter, so L is a parameter we're going to be picking from here. I had an idea, I think it's also important to note, what if L is a specified parameter for each user? So we're going to maybe track the user's average duration of conversations, and then we're going to say, this user tends to be active for 45 minutes, whereas Bob tends to be active for 4 hours, okay? Just kidding. So in that case, their L value will be different, and then I will treat their activity based on their specialized history. But for now, I think it's simple enough for us to be just moving with a standardized fixed L value. Okay, and here I just explained what these are. Also, don't worry about anything. I'll be sending these documents to everywhere you can access this. A gap whose preceding message is unobserved and excluded from return law fitting. These are just fancy words of describing membership leave, unit closure, all of this stuff. So finite rate cap. And I think you guys would be more familiar than me about these equations. Is we have a psi of lambda cap function where we have lambda cap 1 minus e to the negative x lambda cap. This is a function I learned. These are for capping unbounded variables. So say, recall that I said lambda was the participation activity rate, right? So a user allows post 5 posts per minute. That's the rate. That's not a probability. I'm just talking about a rate here. If I want to talk about, put a limit to this, because naturally humans have a limit. I mean, you cannot just say Bob will post 500,000 posts a second. I mean, it's unrealistic, right? So why am I trying to limit this? Because it is likely that we can get some kind of problem, error with that. So we are bounding this by a given lambda value. We're gonna not to increase accuracy or anything. It's just a realistic choice of how much a human cannot be posting in a given time interval, or whatever we're talking about, based on this L. And we say 1 minus e to the power of negative x over lambda. Okay, we need to have this. I think this is also one of the probabilistic. This is a function we have for defining this kind of psi index. So I'm not going to go too deep into it. The transformation is increasing agrees with x to the first. So x is basically going to be our unbounded, uncapped, unsaturated version of lambda. And then we're going to have this in this psi function, as you can see. And sensitivity, these values are mandatory. The participation fitting are basically what we have there. All right, so lambda activity. This is unsaturated. When I have the line, I mean the unsaturated values, so we didn't put these into the psi function yet. How do I define this? Well, this is a baseline of user posts. Okay, this is not, notice how it's different from this. You can say, hey, aren't these the same? Well, for an activity, this is a rate of change. I don't want to say rate of change, but this is a instantaneous rate of posting. This is an instantaneous rate of activity, okay? Activity rate. Here, this is not an activity rate. That's basically a baseline rate. So a baseline rate could be what? How many messages they have posted divided by, you know, the activity period, or whatever you want to call it. We can name this however we want to. This is just a baseline activity rate. Okay, it's not a rate, but it's like, yeah, it's not a time variant rate, I should say. It's not necessarily, we have an average. Okay, treat it as an average. How do I there's also another important thing. We treat everyone's we take the period deviation of this. Okay, so we don't want everyone to have the same kind of activity rate, baseline rate, so we have some kind of deviation where it's centralized at 0, and basically we take this sum and then take e to the power of mu 0 times e to the power of delta u to get this as well. So these are basically some measures we need to use to describe this mu of 0 u, and multiplying this with the exponent of these weights. What are these? So these are the trace values. Recall this was the activity trace. Should I go up? Hold on. How can I show this quickly to you? Recent posting activity, recent direct attention received by user, recent harmful messages. I'm just gonna tell it to you because I don't want to go back and up and forth. So weight of recent activity of user u, weight of recent, what was this? Names get confused all the time. Recent direct attention received by you, okay. Recent thread activity. This is thread heat, actually, I should say. Recent victimization and slow victimization, okay. No, this is recent victimization and this is slow victimization, doesn't really matter. And this is basically the saturated version of lambda. This is the reason we're saturating is because if we don't do this, then numbers get really harder to compare. So another benefit is not only that we limit it by an upper bound, we also can compare these values in a very natural way, because when you do this operation, you're guaranteed to get a value between are you? I think here you get a value between 0 and 1, and you multiply by the lambda cap. Yeah. Anyway. And there is some kind of ridge penalty to fix the statistical deviation. So if a user posted too little and they get either a too high score, you put this penalty, this based on the other people's, like the deviation, and the penalty is selected on model selection partition. So we're going to talk a little bit about that too. This is basically some of the things, but the main idea is here, how are we modeling lambda? The way we model lambda is basically take the user baseline activity. I'm sorry, it's too late. I'm trying to so I've been working on this since 2 days, so I'm sorry if things get a little messy. Anyway, and we get these values with the traces, combine them, and then this is gonna be our lambda activity, and we then normalize it, not normalize it, but saturate this value. And these are also hyperparameters we need to work with. An important model note is that recall what I said about these. This is quick victimization, and this is recent victimization. So this is a fast trace operator, and this is a slow trace operator. Okay. So now, when you think about it, let me give you an example of a problem we can encounter. If they're closely correlated, what happens is we first of all, this could be a negative and this could be a positive. If they're closely correlated, let's say they're 90% correlated. In this case, what's going to happen is our hypothesis we're talking about here is fast victimization and slow victimization have different effects on user participation, instantaneous rate, the time rate, not instantaneous, but posting rate. Okay, so now if we give different weights, we're basically saying these matter in different ways. But if they're the same variable or close enough to be the same variable, if they're 90% or more correlated in this definition, this is going to create a problem where you can just maybe even add these weights, or you can get really absurd results. So to prevent this, why is this specifically special to this two variables but not others? Because one is fast victimization, the other is slow victimization. So now let's post a harmful post to Bob. Bob's victimization score is what? Let's say it starts from 10. It escalated to 10. And then slow victimization is going to be what? 10, 10, 10. After a long period of while, 9, 9, 9, 9, 8, something like that. Whereas fast victimization is going to be like 10, 7, 5, 3, you know. But for the first few instances, it's going to be what? It's going to be exactly correlated. That's the issue we have here. And besides, these are also accumulated results, right? These are trace operators, so we're not only talking about a quick change, but these could be victimized history of user use. So this could be still correlated even though we have multiple different users attacking to user use. So this is a problem, and the way we address that problem is, where is that? Where's that? I think I mentioned it a little down below. I'm trying to find it. Oh, yeah, because if the analysis reports their training and held out correlations together with R-only, V-only, and joint participation fits. If this correlation exceeds 90%, not necessarily a strict result. It could be 85%, 80%. Nothing magically happens at 90%. It's not a strict value. And coefficient signs, so one is positive and one is negative for R or V. And rankings are unstable across bootstrap samples. Only the variant with better selection log is retained. So we just pick one of them, the one that has better results. Hopefully this wouldn't be the case, because the argument we have is the slow trace and the fast trace have different effects, but obviously that doesn't necessarily need to be true. In that case, we can just drop one of these and just go along with these three things to define user activity. Anyhow, now we're talking about an important, very important thing, Weibull baseline. Recall that we have this, recall that we have this function. Where is that? Yeah, anyway, that function, and where key is equal to 1. Did I talk about this? No. This is a survival function. Okay, this is where we are expecting a failure. So when could a failure happen? A failure could happen when a user appears. That's basically the hazard we're talking about here. It's not necessarily a failure, but by the statistical language, I stick to those terms. So if k is greater than 1, in case we also should probably test that, but I'm quite on the side that this must be a positive, greater than 1, because the user's participation seems to be some kind of hazard function. Alright, because I mean, it is a hazard function, but when they appear, it is the moment when they're gone that increases the likelihood of that events happening, or harm happening, or they appearing again. So tau is basically how long they have not been posted, so the time between their last post and the current time. K is a number we define, and theta is also a number we need to select. It's a global scale gout, so this is basically for globally return rate. We're trying to find an optimal result, an optimal parameter for everyone in this survival function. Now this is where the UTC idea comes from, the time zone. Why are we doing this? This is a Fourier series with expressing the time of the day. Okay, we have 24 hours in a day. This 2 pi is part of the function. J sub c is going to be explained, and we have these coefficients and cosine and sine. These are part of the Fourier sine series. I'm sorry, the Fourier series. Okay, and J sub c, this top part of the summation, is a number either 1 or 2. So we can define this in 2 ways. We can this supposed to, let me explain it much better. AJ and BJ, right? These are values we're going to be selecting based on what we think, or maybe some kind of machine learning algorithm could also learn this. We're saying that at 4 a.m. someone would not be likely to post, or 5 a.m. they're not gonna, but at 1 p.m. they're gonna be likely to post. Well, obviously there's well, right now we're not defining this as negative, so we're still gonna give a weight, but probably likely we're gonna give a higher weight for more likely time zones. Okay, for 5 p.m. in the evening, it's more likely, or 4 p.m. in the evening, it's more likely. My suggestion was previously that we could make this user specific, so the likelihood of posting would also depend on their time zone, and that's a longer process, but I think it is a more personalized variable and probably maybe more descriptive, but it's still okay to stick to that. So why 1 or 2? I'll notice if I plug 2 to J, this becomes a 2 pi over 12 hours, and this is a 2 pi over 12 hours. So this is now splitting this case into 2 summations from 1 to 2. So we're gonna have a one series of 12 hours, another series of 12 hours. So we're basically splitting the time of the day. It could be convenient for several reasons, but I think right now it is a good idea to stick to 24-hour zone. And this is just gonna give us a value, and this value is gonna help us determine, we're gonna use that value, the row of C is multiplied here for the return activity. Oh, it is important to mention, the part I'm talking about is for an inactive user, okay? So the user has been away for at least L time. What is L? Let me go back. L is one of these times we defined here. So if a user is gone for at least an hour, let's say we picked 1 as an L, if the user hasn't been active for 1 hour, then we are classifying them as inactive, okay? So if they're active, this is how we find lambda, okay? This is lambda active, okay? If they're inactive for more than an hour, or whatever we choose, this is how we get lambda, the activity rate. Because now we have 2 different cases. Either they're active now, they're likely to post again, and now we can contribute all of these trace operators into the likelihood of posting again. They mentioned I don't know, all of these trace operators become relevant, but now the relevancy really changes, because now we don't necessarily have the same trace operators we had before, because they're gone. And because they're gone enough, we are now using a survival analysis hazard function, a Weibull baseline distribution, to plot when they will be returning. So their now new activity rates will be depending on this part of that, and that's time of the day. Also, and if you're unhappy with the complications that come with this, I think we can remove this. This is not probably an essential part of the what we have here, but still needs to be discussed, I think. And then we get this function, okay? So what is this? This is basically this survival analysis function, if they're likely to return again or not. The time of the day weight, okay? So if at 5 p.m. I'm going to give 1.5, for example, and 4 a.m. 0.5, and exponentiate this function, okay? What are these? Well, let's see. Oh, okay, here it is. This is the deviation of the user, okay? So the baseline deviation of other users' baseline posting. So we still use the idea of baseline post rate from the given history to us, okay? So now this is a deviation for returning users, and then we're multiplying this with a return rate for JFU. What was JFU? JFU is a recent direct attention received by you through replies and mentions. Okay, I mean, you can be gone, but you can still receive mentions or replies to your comments. Okay, and RFU is fast recent victimization history of you. Slow shouldn't be playing a role because slow is not changing, but what could potentially change is while you're gone, someone can target you with throwing you a bad message. I mean, these are really, anyone could argue these are not very likely, these wouldn't happen, and I totally agree, we cannot just say these are true. So these are hypotheses, and that's why I put these unknown values, these unknown variables, so we can also test that, see that, and tweak it however we want. And now we also do the same thing where we did limit this with lambda cap. and we get this return rate, this return uncapped version, and now we saturate it, and now we get the lambda return rate. Okay. Let's see. Also, it's why is it good to use the Fourier sine series is a question someone could ask. It's because these are creating a circular shape, okay? And the time of the day is a circular shape. At 23 military time, if you add another time, 2 hours, now you're not talking about 25 hours. It's like making a modular arithmetic case where you go down in hours. So this is actually a very nice way to plot the time of the day using Fourier sine series. I mean Fourier series more accurately. Why is this process well posed? Well, here is the limitation we had to. This is an architecture problem, by the way. This is not necessarily we invent. This is just by design choice. It has to be well posed. The idea is that the capped version must always, okay, always be greater than or equal to what we have. So we are basically, as we use in the psi function, we have to make it work with all numbers. So we have to have first of all reasonable numbers and then comparable numbers. So this psi function helps us normalize this in a way, standardize this. And the idea is, since look at this, this psi function always ensures that what does it ensure? It ensures that the capped value, the saturated value, must be greater than x. Okay, I mean, after you transform it, x, we all have only saturated lambda values, is what I'm trying to say. The saturated lambda value is not necessarily greater than x, actually the opposite, but we are making it so that this new value is now less than lambda cap itself. This is lambda cap function. Okay, so, and how does it prove it's well posed? So to prove this is well posed, the idea is every user has a fixed value of posting, say 50 messages per hour. Okay, this is a capped lambda version. So I'm saying they should not exceed 50 messages per hour, or whatever you want to say. Now you sum it for all users. So for every user, multiply the average, not the average, but the sum of the harmful. I'm trying to find words. I'm sorry. It's too late at night. I have 50 messages per hour toxin rate. Dr. Anand has 50 messages. Dr. Sartaj has 50 messages. We multiply this by 3. So in this thread, I cannot have more than 150 messages per hour. That's a simple limitation I put on this data. And the sum of this is basically telling me for lambda values, sum it for all users. So these are individual rates, right? These are individual rates. We computed this. These are all specified with traces and all of that stuff. So when you sum this up, it's always less than this. Why is it always less than this? It's a good question, and it has a good answer. So for lambda u, how do we define lambda u? It's 1 if and only if. Now we put two cases. Either they're inactive for a while. If they're inactive for a while, we take this return rate. If they're not inactive for a while, we take this. Okay, so it's eventually boils down to one of these formulas. So this is less than lambda cap itself because we already put this in the psi function. Likewise, that's the other case. So these are not very important details, just they're not inconsistencies with the mathematics here is what we're trying to say, and this is the proof of it, explaining it's not inconsistent, it's well posed. Message level harm and collision hypotheses. So you might recall this structure. These are the Z tables. So this is actually doing the same thing for traces. We want to have we don't want to, like for a data set, you could have a thread heat for 500 heat toxic messages per second. It's insane. Some data sets could have much less. So you put this in the Z distribution. What is the Z distribution? I'm pretty sure you guys know this a lot better than I do. Z distributions table. You can always skip these parts, by the way. I'm just showing it in case it is helpful. It's a table like this. We normalize our insanely huge variables or numbers with plotting it into a thing with 1 and 0, 1 and -1. And we get small z values, and we have a z table for it. Is the function here? Anyway, I'm not gonna search through this function a lot, but this is how we compute the average x, small x minus the top average, and these are training values. So these are training only means for machine learning, and then you divide with the standard deviation scale, and this is how you get these small RU values where you plot it into the z table. If scale is 0, the corresponding feature is removed. Why? Because at scale at 0, you don't want to have a division by 0, right? I mean, that's the case. This is just to avoid mathematical inconsistencies. And now here comes the important part. I don't want to block it. This is my collision hypothesis. I'm going to talk about this. This is a very important part of the model. Model is saying now, okay, we know that given a user post at t with all the information I have, this means all of the information we have as inputs before t, or t from approaching from the left, or f of t, whatever you want to call it. Given the set is not empty, what does that mean? This means that the probability of we don't have an empty target set. What is the target set again? The target set is basically, if the target set is not empty, we mean that someone is being targeted within a message. So it's a harmful message. Okay? The probability that a target set is not empty, given the fact that you post at time t. Okay? So we need two probabilities. This is the Bayes theorem. We have the probability that user u posts at t, given the probability that user u posts at t. What is the probability that t is not an empty set? There is a harm going on here. You put and this is my notation, I use q of t for the harm rate of the user u. Okay, you get the sigmoid. Sigmoid is basically how we can get a value that ensures that we have a value from 0 to 1. And this is how we get it. So B0U is basically something similar to the baseline rate. This is for baseline harm, and this is for deviation. A of E is a standardized value for E. And this is the thread heat going on. I just want to go back to it. Recent harmful activity in the conversation as a whole is E. Okay? That's E. R of U is the recent victimization of user U. G of U, and these are, by the way, just hyperparameters. G of U is the authored harm by U, and this is the collision hypothesis, and this is where the model comes into place. Xi is just a parameter. The conversation heat multiplied by the recent victimization. So this is what my ship analogy was referring to. If a conversation is heating up, okay, a conversation is heating up, and a user is easily provoked. So if they have recent victimization in a heating up conversation, the conversation is heating up and someone is getting victimized too. So these two variables are both increasing. So the question, or more specifically the hypothesis I have, is the more one of them increases, the other one increases too. This is not a linear function anymore. Notice how all of these pieces are linear. It increases linearly. This is not linear. This is an exponentially strongly growing model. So this grows quicker. So I'm trying to say that the heat of the conversation also increases the recent victimization, and the recent victimization also increases the heat. If you want to see what I mean, you can take the partial derivative of the logit. This is the logit. With respect to E, you get A plus psi RU. This is the partial derivative of this function. So this means that E depends on A psi RU. Okay, so the more you increase RU, you're actually increasing the rate of change with respect to E. And the same thing goes for RU. If you take the partial derivative of this with RU, you get B plus psi E. So increase in E also increases RU theoretically as well. This could be a false hypothesis, which is why this is my I thought this is my model, this is what my hypothesis is. So we have to also test this and see how this performs. So these are 4 model ideas. This is because this is the heart of the model. These are the model ideas. So what are we trying to compute here? We're trying to compute QT. The given probability that someone is posting, what is the probability that someone will be harmed? There are several ways to do this. Model 0 is basically saying, just take these 2 parts of this sigmoid, okay? Model 1, I'm sorry, this was model 0. So model 0 says that heat of the conversation and recent victimization has no effect on our model, or very small effect such that it could be ignored, and we can go for use in model 0. Model 1 excludes the hypotheses we have, so we basically don't hypothesize this. And why would we want to do that? These are really close enough such that we don't even need to compute this. It's now unnecessary information, or maybe it's the return is not good enough, or it's maybe even performing worse. Okay. M1X is basically the model I just introduced to you. M2, M3. So M2 is basically without the hypothesis, but saying that these are not necessarily linear functions. So these functions could be, these are cubic functions with 3 degrees of freedom each. Okay, we don't want to increase the degrees too much, because after a certain point it's going to be very hard to solve these equations. So and getting more complicated. So S3 can be, these can be cubic as well at most. Okay, maybe a quadratic or a second degree would be enough too, or for either one of them. We just define functions of S, and this is the same version with our collision hypothesis. I just talked about the correlation shouldn't be greater than 0.9, and candidate targets. So this is where the third part of the model comes up. This is trying to compute pi of UV. Okay, so this is still a process that is going, and I'm not really confident about what we have in this part of that, so I'm not gonna be defending it very strongly. But the idea here is pretty much this. The reason I'm not so confident is because the assumption is if a harmful message is sent, it will contain a target set of users. So now the question is, what is a harmful message? What does the data set, what does the inputs give me? Are you just giving me toxicity scores? Because if that's the case, toxicity scores is not enough to say that someone is being targeted. If you're giving me harmfulness scores, like genuinely this is a harmful message towards somebody, then yeah, then the model is not very flawed, but the inputs are now need to be more well defined for this to be able to move forward. So we have the let RW be the contain users who post or reply to or mention. So these are active users, active online users during this time window, T minus W to T, open time window. Why? Because we are forecasting at T. Okay, we cannot have information from T even T. Okay, before T. The eligible named candidates for author UR BFU T equals to. These have to be in the members set. Okay, remember in the very beginning of the paper I defined what? I defined the members over here. These are the members who have joined the chat, and this is a stage 1 model, so we are considering this as a closed node, so we're not actually introducing new guys into this party right now. We're just treating that as a constant finite set of users. The other one is also finite, but this one is not necessarily changing right now. So among these users, we take one user, excluding the author himself, and now these are, by the way, candidate target, not necessarily a candidate at this point, but we're looking for candidate sets. We're trying to reduce here's the thing, we could have a 50,000 user chat. You don't want to go through 50,000 people. I'm pretty sure that's computationally hard. So we can reduce that set to a smaller subset of people who are likely to be targeted by this message based on what information we have, to get a smaller set. And the smaller we get to a set, the more easily moderative or computationally easier it becomes. So the V also must be an active user for this time to be eligible to be a candidate, or either one of these requirements must be passed. Okay, so either there is a slow directed harm history between U and V that is greater than epsilon D. This is what we need to define as a machine learning hyperparameter kind of thing. And slow victimization, was it slow or quick? I think it was slow victimization. Slow victimization history. Let's see. Slow victimization history is greater than some value. So they accumulated enough victimization historically to be a target, or the user commenter, the author of the message, have directed harm against them that is greater than a certain threshold, or or the user is currently active. So it doesn't necessarily need to be currently active, but if they are currently active, they are members of the candidate set to be the candidates of the candidates. So the eligible people who to be candidates. Okay, so either of these three are people who can be candidates. For V in VU, define a deterministic pre-message ranking order. So now we're scoring everyone. Okay, we're giving points. This is a score to be a candidate. 2 points if. This is a if operator. 1 if true, 0 if false. V was directly replied to or mentioned in W. What does this mean? In this time zone, W, V was directly mentioned or replied. We get 2 points. Why? Instinctively, I think that if you're currently active, if someone's going to produce harm to you, you need to be active and they need to talk about you, right? I mean, that's the easiest one to catch. It should be easiest one to catch. So because of that, I think it's reasonable to give this a higher score too. But yeah, we can play around with these values to make everyone happy. +1 if V posted in W. So if V posted, they're also giving some vulnerability, because now maybe they said something stupid. They just posted. Everyone can now jump and kill that guy. Okay, so that's also one way to get a point, but obviously this is not strong enough compared to being specifically called out in a chat. Plus logarithm of, you add this 1 to avoid having an undefined function, and then you get this fraction. What is this fraction? D of U to V. So there is a history of targeting between U through V. The author targets this user historically, then defined divided by some training positive values. The medians of positive values replaced by 1 if none exist, and victimization history of V in history, and these are computed in a logarithmic way to add scores. So the cases, the problem someone could raise is, what if they get a tie? So the reason I incorporated logarithm is to avoid that, so we wouldn't necessarily have a tie, because at that point it's very hopefully going to be unlikely, because of the trace values and these specific variables. You shouldn't get the same points by somebody else because of these two factors. I mean, you could get these two same, but these two should be different. It's the main idea. So there will be a hierarchy of scores between the users and BFU. And you get the candidates set by selecting the top K users, okay, top 20, top how many you want. These are some suggested values for K and some suggested for window. Tops how many users in this with this point, okay? So if I have 100 points, Bob has 90 points, Alice has 80 points. If I'm looking for the top 2, it's me and Bob. So we exclude Alice from the candidate set, and now these top values become a part of this set. Okay. These are some ways to deal with other, so people who are outside of the candidate target set, so they're maybe not even active, or any of these requirements. They're outside of these requirements, outside of BFU, basically, outside the named candidate set. And then we define these to figure that out, but that's getting more and more specific, such that we don't really need to. I mean, before we move on to this part, I want to make sure that we can agree upon what we have here. If not, we can go back and fix this. So I'm not going to dive too deep into what we have there. The message severity is defined by this, where this is the user's history of sending a message, harmful message. This is the number of messages, average harm of the messages, global, and all of this other stuff. We get message severity. Okay, and forecasting outputs. So, oh my gosh, it's getting too late, honestly. 11:30. This is a probability. So what we have is a closed mode. Okay, given this information with no deterministic trace, and tau equal to L. So crossing tau equal to L. So they are inactive at this point. How do we do? How do you find exact first message quantities? The exact first message quantities are useful for us to compute important ways. For example, what we are trying to look for is the first, let's say the first toxic message, the first harmful message in a thread. How can I do this? Let's define the activity of posting activity of lambda. Okay, for users, we already defined them, so we know. And this superscript means that there's no messages posted until this, assuming, with the assumption that there will not be any messages posted. And this is for everyone, for everyone's rate. Okay, then probability of no message in t through t plus delta, given that we have all of this information, is what? E to the power of the negative integral from 0 to delta, where delta is the future we're trying to forecast. It could be any value you want. Why do we get this? Well, the reason we want to, and this is coming from a statistical property, e to the negative 0 to infinite delta. This is a very commonly used function for density, and we're plotting this for the probability that there will not be any message with this information. And probability of first messages by you and harmful by delta, given this information. So how do I say this? When I want to say Alice will be the first one, what is the probability that Alice will be the first harmful poster? Alice will be the igniter, in other words, and the only first person. So you need two things. First, there will not be anyone posting until delta, and Alice will be not only posting, but also posting a harmful message. So this is the probability that no one will be posting until delta. And this is the probability that Alice, this is posting rate, times Alice's harmfulness rate. Okay? And you need to multiply these, get this integral, and multiply it with this. Okay? And this will give you the probability of first messages by you and harmful by delta. Author only harmless and conditional versions follow through the same substitution. So if you want to find the harmless version, drop this Q. If you want a conditional message, you know, all of these substitutions can give you what you're looking for here. I'm not going to talk about the open mode because this is where we need to first verify stage 1. But you get the idea of open mode. And here are some information on ideas on what we need to do. This is the instantaneous expected reheating rate of a conversation. So the instantaneous, this is the message severity as we discussed, the harmfulness rate, and the lambda is the participation. And this is for the entire thread. So you're summing up for every user. Okay. And yeah, these are the inputs we are looking for, some basic information on what we need and what means correct data here. So this is the collision model. Please let me know if you have any questions, and if you have any opinions about this model. I'm very happy to discuss this, but I like the way this model is looking right now, to be honest, and this is what I'm presenting. So let's see. Okay, thank you very much for watching this video. See you tomorrow. I have to get some sleep, and let's discuss this in the meeting if you have a chance.